I'm very proud of my different marker colors. Here's to hoping you can see them. All right, so I'm going to start with the basic Bernoulli equation. Pressure at point 1 plus density, gravity, height at point 1 plus density 1/2 density velocity at point 1 squared is equal to pressure 2 plus density, gravity, height at point 2 plus 1/2 density velocity at point 2 squared. Where's point 1? I'm going to choose point 1 to be the top of the water, and I'm going to choose point 2 to be the hole. That's 1 and 2. You are allowed to do pressure in either gauge or absolute, but either way, both these points are touching air. So because they're both touching air, both pressures are 1 atmosphere. That cancels out. This water is moving awfully slow, very slow. In fact, if this water moves as little as 1/10 the speed of that water, just 1/10, that 1/10 gets squared to 1/100th, and 1/100th, when one term is 1/100th as much as the other term, it's worth throwing away. And that's not even the case. This is going like 1,000th as fast. So 1,000th squared is 1/1,000,000th, when the velocity 1 squared is 1/1,000,000th as much as velocity 2 squared. That is so little, let's just cancel it out. Okay, and your students need to be able to argue this. When they write Bernoulli on the AP exam, they have to be ready to give a verbal argument. Why did they cancel out these terms? Height number 2, I'm going to define that to be the origin of height. That is the origin. That is where height equals 0 is for Bernoulli. So that's going to cancel out this term right here. And what I'm left with is density, gravity, height 1, which is just the height of the water, so I'm not even going to call it 1 anymore, equals 1/2 the density of water, v squared. Let's let just v be the speed that we measured. The density cancels out, and you can multiply by 2 and take a square root. So when you do, you get velocity equals square root of 2gh, and that is the source of the square root we saw, where velocity versus height was a square root function. So make sure you're going through this idea with your students, and they showed the evidence. Now they need to tie it back to the Bernoulli equation. All right, so that's all good. That's Bernoulli Lab number 1. Okay, Bernoulli Lab number 2. Now I want to see how fluid speed depends on pressure. Lab number 1, how does fluid speed depend on height? Now how does it depend on pressure? So the relationship between the force on a fluid and the speed that the water emerges from the hole, we're going to use a syringe that has a very low friction plunger. This is saline solution. My wife is a nurse, and she doesn't have a problem using these syringes. They're going to throw them away anyway after the saline solution's out. So I said, hey, can you bring home some of these saline solution syringes? They have a very low friction. They're very nice. So what do? You ask around. Hey, anybody here a nurse? I have a parent who's a nurse. Your students aren't a nurse, or else why are they in school, right? Anybody here have a parent who's a nurse, a doctor? Hey, does your mom or dad, can you find out, or maybe you can place a phone call home. Hey, Mrs. whoever you are, Tommy told me you're a nurse. I have a question. Is there a way you can get me some syringes that would otherwise be thrown away? Like, can you collect them for me? Have Tommy bring them to school? I have a really cool demo I'd like to do with them. Maybe ask your school nurse. I don't know how often they use these. Syringe. Ruler, stopwatch, and a caliper, different weights. Okay, so what are we going to use with these? Remember, I'm trying to step out of the way so you can pause the video in order to write down things that are up on the board. Okay, you're going to use a little caliper, get the diameter of this little tiny hole. Good luck with that, by the way. Maybe you need to hold it up to a meter stick or something. I don't know. Figure something out. Okay, hey, you know what you could do? I have a better idea. You can make the students experimentally determine, maybe back when you're teaching continuity, can you experimentally determine the area of this hole? if you can, or the diameter or whatever kind of thing, then how would you do that? Well, you do exactly like we did with the big squirter. With this big squirter, you just get a distance that the plunger goes, a time, and a projectile motion, and then you can solve for this area, assuming you can get this area, and use AV equals AV. Okay, use a caliper to get the diameter of the syringe barrel and the needle. Use geometry to turn those into area of the barrel, area of the needle. You just need to get those two areas. You're going to attach the syringe to a burette clamp facing down. I don't have a burette clamp right here, so I'm just going to use my hand. Okay, so you attach this to some kind of a clamp, all right? You're going to fill the syringe with the known volume of water. I mean, it says the number of milliliters on the side. And you're going to set a mass on top of the syringe. Time how long it takes for the syringe to empty. So you're going to know this volume. You're going to use a stopwatch. You're going to go beep, or whoops, beep, beep. Your students may need to exert some support forces to keep the mass on the syringe, but they should not push down or pull up. This is a known amount of force, M times G. And we can get the speed of the water in the barrel using distance over time, and we can get the speed of the water coming out of the barrel using A times V equals A times V. Okay. So, vary the amount of mass set on the syringe, thumb rest on each trial. Use continuity. You measured the volume, you measured the time it took for the volume to emerge. Set that equal to the area of the needle, which you knew in advance, or you measured in another experiment, times the velocity. Oh, and then solve for the velocity of the water coming out of the needle. Then use pressure equals force over area to get the pressure of the water on the barrel. Now, this is a gauge pressure only, not an absolute pressure. An absolute pressure would be mg, force, over the area of the barrel, plus 101, was it 101, 300, something like that. 1 atmosphere of pressure, right? I would encourage you to do this entire lab in gauge pressures. Okay, so that's what you're going to do there. So, what data you're going to take? You have constants, area of the barrel, area of the needle, and the volume that's going to come out. The variables are going to be, you're going to vary the mass, and you're going to get a different time, and you're going to use the M to calculate the pressure, and you're going to use the T and these up here to get the speed of the water coming out of the needle. You'll get pressure and the speed of the water coming out of the needle. Those will be your variables to graph. Okay, so here's the diagram. Mass goes on the thumb rest. Pees the water out. There's the plunger, and there's what's called the needle hub, or you can just call it the needle if you want. Here's the data that I took. I did this on a different syringe, a 60 milliliter syringe that I actually ordered. But if you want to do that, you can. However, these are probably easier to get a hold of. These are just little 10 milliliter suckers, and they work better for this video. All right, so I tried different amounts of mass. Notice as the mass increased, the time it took for the water to come out decreased. That makes sense. The pressure is mg over the area of the barrel itself, and the water speed was calculated using continuity. Then what I did was, okay, is 0, 0 a data point? Well, if you have no pressure pushing your water out, then you got no water speed. So yes, 0, 0 is a data point, and you get that nice square root curve again. You get the square root curve again. Your students should look and say, oh, that's a square root curve. Are P and V directly proportional? No, because directly proportional means that the two variables make a straight line through the origin when they're graphed. That is what directly proportional means. Yes, pressure goes up and speed goes up together. That does not mean directly proportional. Directly proportional would be a straight line that passes through the origin. This is a curved line. That's curved, so not a line. All right, so what should they look like? They should look like a square root curve. I'd like to show you why that is now, using my nifty markers. All right, start with Bernoulli again. Pressure 1 plus density, gravity, height 1 plus 1/2 density, velocity 1 squared is going to equal pressure 2 plus density, gravity, height 2 plus 1/2 density, velocity 2 squared. What are my 2 points of interest? I'm going to let the inside be 1, and I'm going to let the needle be 2. I am working in gauge pressure. Gauge pressure means that the atmosphere exerts no pressure. Pressure 2 is the atmosphere. Engaged pressure is no pressure at all. However, pressure 1 is going to be mg divided by the area of the barrel. That's pressure 1, force over area. The speed of the water inside the barrel of the syringe is so slow compared to the speed coming out of the needle. It's less than even maybe 1/20th. 1/20th squared is 1/400th. That's too small to notice. Make sure your students understand why the speed inside is so small compared to the speed here. It doesn't really count for anything. Is this, I mean, this is not even 10 centimeters. Have your students actually calculate a 1/2 density velocity squared. Actually, like plug in numbers. Then have them plug in a density gravity height with, what is this, 5, maybe 7 centimeters? The rho GHs will be so small, not even worth considering. So the rho GH is actually very small for this lab because the syringe is so small. Okay, so what are you left with? What you're left with is pressure 1, mg over area of the barrel, equals 1/2 density velocity of the needle squared. Let's solve for the velocity at the needle. Bring up the 2, bring down the density, and square root. The velocity at the needle is then 2 mg divided by density and the area of the barrel times velocity, and that's it. That's all there is. Take the square root. All right, so what do we see? As the mass increases, the velocity increases, but there's a square root. So there's a square root involved. Or you could have just left it in terms of pressure. Then you get 2 pressure over density. Gosh, you need to teach your students to write these two things differently. The P for pressure and the rho for density. Please have them write those differently. And again, the bottom line, square root. That's why we got a square root curve. Try these two things yourself, and if you can get good data, inflict them on your students. Okay, then after they learn Bernoulli's equation, I engage them in certain activities. One is a squirt gun activity. All I want to know from the students is this: how much pressure do you put on the water inside the squirt gun when you shoot it? How much pressure is that? So what the students are going to do is they are going to measure the projectile motion of the water, its initial height and the horizontal distance it goes, and use that to find the speed of the water coming out. And then once they get the speed of the water coming out using projectile motion, what they're going to do is they're going to set up, and I'm going to use a blank screen for this, they're going to set up pressure equals, pressure plus density gravity height plus 1/2 density velocity squared in the gun equals pressure at the nozzle of the gun, density gravity height at the nozzle plus 1/2 density velocity at the nozzle squared. The inside of the gun and the nozzle are at the same height. So because they're at the same height, that cancels out. The nozzle is at atmospheric pressure. Let's use gauge pressure just to eliminate that, make that 0. The speed of the water inside the gun is super small, so they use projectile motion to get the speed of the water at the nozzle, and then they solve backwards for the number of atmospheres of pressure, the number of pascals of pressure they exert on the water. This is usually between a half and an entire atmosphere, 50,000 to 100,000. Cheap crap from the Dollar Tree. That's what that is, just cheapo garbage from the Dollar Tree. Here's another one I do with the students. I give them this pipe and a meter stick, and that is all. They need to make calculations in order to find out, and I tell them, I'm going to put a desk near the drain in my classroom. We all have emergency showers, right? The desk is near the drain. They're allowed to walk up to the desk and measure anything about the desk they want and measure anything about this pipe that they want. But when they're ready, they're going to set the pipe vertically. Notice there's a hole in the pipe, and only one end is capped. They're going to set the pipe vertically on the desk. They can move the desk anywhere they want. They're going to plug the hole, fill the water up with a little pitcher all the way to the top, and when the water comes out, it has to hit the drain and not make a mess. So in that case, they're going to use Bernoulli to solve for the water coming out, the speed, and use projectile motion to see where it lands. All right, so that's another one I do. One more thing that I do with students is I have them do what are called Bernoulli bar charts. So if you don't mind, I'd like to tell you about Bernoulli bar charts. What are Bernoulli bar charts? Well, first of all, I teach the students energy bar charts back in Physics 1, where we have, let's say, kinetic energy, potential energy, and other forms of energy. And maybe you're moving and you have some height and there's some other form of energy. And then let's say you go down in height, so that means you speed up or something like that. I'm having them do these bar charts for energy. Representations matter. Well, for Bernoulli, I have them do Bernoulli bar charts where it's pressure, rho g height, and 1/2 rho v squared. Pressure somewhere else, rho g height, and 1/2 rho v squared. So, when would they be doing Bernoulli bar charts for me? They would be doing Bernoulli bar charts to talk about the water peeing out of here. So, inside here, at the water level, inside the bottle, you would have no pressure, or you would have it exactly at 1 atmosphere or something. So, is it absolute pressure or is it gauge pressure? You have to choose. There's height of the water inside the barrel, but the water's going super slow. At the hole, same pressure, no height at the hole, so that rho GH became 1/2 rho V squared. Now I know what you're thinking. Wow, that's really boring. Are you going to have them do that for the syringe as well? Yeah, I have them do it for the syringe or for the squirt gun like that. But let's talk about some more interesting situations. Let's talk about a Bernoulli bar chart when you are drinking water through a straw. Okay, so let's say this. Okay, there we go. There's the straw. And I'm going to choose points maybe 1, 2, 3, 4, and let's say right here 5. So what are the Bernoulli bar charts going to look like for each of these? Pressure, rho g height, and 1/2 rho v squared. I am going to choose for this right here, 2 and 3, that's going to be where height equals 0. So 1 has air pressure on it, and I'm going to draw a special line. You have to do this in absolute pressure. So I'm going to draw a special line here for 1 atmosphere. The pressure at 1 is 1 atmosphere because it's touching the air. The height at 1 is something. The speed at 1 is 0 because that water is moving very slowly. It's in a big cross-sectional area. What about 2? 2 has a lesser height, so 2 is above atmospheric pressure. 2 is above atmospheric pressure. Okay, height equals 0 at 2, so this is above atmospheric pressure. What about at 3? Well, 3, the water's moving. Remember, the water at 1 and 2 aren't barely moving at all. But at 3, the water's moving some. The water's moving some at 3. So that takes away from our pressure. Does that mean the pressure is equal 1 atmosphere at 3? I don't know that. I don't know that for sure. I think that the pressure's still a little bit above 1 atmosphere. So then that means that this velocity is going to be something. In fact, if you don't mind, I'm going to now start defining units. 1, 2, 3, 4, 5 makes 1 atmosphere. And so this is 2. So at 2, all 1, 2, 3, 4, 5, 6, 7, 8 bars would be over here. So this would be what it looks like at 2. Here's what it looks like at 1. Notice it's always going to be 8 bars. Here's what it might look like at 3. What does it look like at 4? Let's see. At 4, we have the same height that we had at 1. If I remember correctly, that was 3 of these. That's the same height that we had at 1. Speed's the same pipe, so we got to take those 3 away from pressure and just see that at 4, the pressure of the water is actually less than 1 atmosphere. Let's go up a little higher. Let's add 2 more here. A little bit higher, rho GH. Then you lost 2 here. And the pressure here is less than 1 atmosphere. That makes sense. You have to suck the water out, which means you have to produce a lower pressure than 1 atmosphere in your mouth. Have your students talk about these everyday processes with Bernoulli bar charts. Okay, I'm going to show you one more activity I have them do, and they have to Bernoulli bar chart it. Okay, here it is. The water bottle, when the bottle gets a hand put over it. Let's have a look at what that's going to look like. Ready? Here we go.